high school joke. Hair part is it just right for you? I thought it was gonna take you. Yeah. Oh, it's on my note. I thought it was gonna be like before you were. No. I said I'm anticipating. I can feel my fingernails still shining. I want 2 hours of sleep. Did you finish the journey? Let me make that choice. You make your own choices. You did. I told you you don't have to go. I told you.
Okay. Is that clock? No, just a smidge fast. All right, so I want to just recap. Did you guys love my nasty email? It went from like 44 views to 92 views, and I was like, we only have 70 people in the classes. Maybe people watched it twice. Anyway, thank you. So I just want to recap the electronegativity and bond polarity because it is kind of a difficult concept, and we're going to have to apply it to molecules soon that have multiple bonds. So think, water, it's going to have 2 bonds that are polar covalent, and we have to think about how that affects the molecule as a whole. So I want to make sure that we're clear before we move on to that soon, probably in chapter 11, that we're clear on what a polar bond is to start with, okay? So this all relies on the idea of electronegativity, which the table is in your exam equation sheet. Let's switch over right here, okay? So nonmetals, fluorine, highest electronegativity. Remember, these guys are really, really small. So they're really small. They can attract electrons because when those electrons come in, they're close to the nucleus. So they're lower in potential energy. So it's like a preferable state for them to be near those small atoms. And when you look at these numbers, you could kind of just think about them as how strong the atom is in attracting electrons. So think about this tug of war analogy. If I've got, I'm going to use hydrogen and fluorine when we go back. So if I've got hydrogen and fluorine, that fluorine is so strong that it's going to pull more of that rope in the tug of war analogy, okay? That rope being the electrons. So the electrons are going to spend more of their time over by the fluorine than by the hydrogen. So in the example here, let's pretend that this is just 2 fluorines. This is fluorine and hydrogen, and then this is fluorine and sodium, okay? So when they're the same atom, or if they're slightly different electronegativities, so the classic example of this is carbon and hydrogen, because these guys have a difference of 0.4. I think carbons, on your chart, they might be actually 0.3, because I feel like it says 2.2 for hydrogen. I've always thought of 2.1 for hydrogen, but it's 0.3 or 0.4. The point is it's really small, and so it doesn't actually exhibit a lot of the properties that we would think of as a polar bond. So either they're the exact same atom or have the exact same electronegativity, or they're very, very close electronegativities. Those electrons are going to be shared equally. Think about them as having the same strength, okay? So the little blob that's drawn there is to represent the negative charge. So the negative charge is divided equally among those 2 atoms. So we would call that nonpolar typically. The fluorine hydrogen one, now we've got that strong fluorine, that's 4.0, and I guess this says it's 2.2. And so the difference there is 1.8, so it's very high on the polar covalent bond side. So the fluorine is very, very strong, pulling some of those electrons towards it. That's why the blob looks bigger on the fluorine side than it does on the hydrogen side. But it's not all the way pulled over to the fluorine the way it would be with sodium, okay? So the way we represent that some of it has been pulled over, and I don't mean like represent it as a drawing. I mean, if I'm drawing the Lewis structure and I've got this, I want some way to designate that this is a polar bond and which side is negative and which side is positive. That's when I'm going to use these partial charges to represent that. So if I was drawing fluorine and sodium, I could say F minus and Na plus. That's because it's a full negative and a full positive. Whereas in the polar covalent, I just want to indicate that there is a partial negative and a partial positive. So this is some number of amount of negative charge that's less than 1, okay? Depending on how big the difference is. If there was a really small difference in electronegativity, maybe like, so maybe not C and F. How about oxygen and fluorine? Okay, so that one has a difference of 0.5. There would be a very slight partial negative and partial positive. The negative being on the fluorine because it's more electronegative. Okay, so it's how much of that rope did the stronger one pull over. Okay, all right. I think that's all I want to say on that. Anybody clarifications or anything? Okay. All right, so moving along, today is going to be a lot of practice. So you guys drawing some Lewis structures, checking the structures together, and then we're just going to add in like 1 or 2 new ideas. And then Friday, same thing. We'll do lots of practice, add in 1 or 2 new ideas with formal charge. All right, this list of steps is what I used to use, like how I used to describe how to write Lewis structures. And I have found that I like my new way so much better. All right. So if you happen to watch a video and they're like adding up the total number of valence electrons and subtracting off something and figuring out how many bonds they are, this is what they're doing. I probably will stop putting this in the notes eventually, but I feel like if you guys watch one of those, now you just know it's this other method. You can look at that. If it makes more sense to you, I kind of don't think it will. But if it makes more sense to you, you've got the steps there. The thing we will use is the idea of formal charge. Now, this is like a very official definition of formal charge and description of it. I'm going to show you how to use it and when to use it a little bit more, just explain what it means rather than turn it into like an equation, okay? So they're there if you want them, but you probably don't need this slide. All right, so the first 3 molecules, NH3, CCl4, and C2H4, I want you guys to go ahead and start in on those. And what we're doing here is the very straightforward approach is we are writing down each atom's valence electrons, and then we're bonding them to satisfy the duet rule and the octet rule. Duet just meaning that hydrogen needs to have 2 electrons surrounding it. Octet meaning the other atoms need 8. Or an easy way to think of this is it needs 4 pairs. So this could be bond or lone pairs, but 4 pairs total. Okay, so start in on those 3. As you're working, I'll go ahead and write NH3 up there. If you're like totally lost, you can follow along there. But most of these should be fairly straightforward. Okay, so I'll set like a 3-minute timer and then we'll talk through these. Remember, the valence electrons are just coming from what column it's on in the periodic table. Okay, I'm not sure if that was too short or not. All right, so for NH3, there is no other possible way that I can imagine you could do this if you're following the octet and duet. So hydrogen can only ever have a single bond. You can't have hydrogen bonded to two things. You can't have any lone pairs around it because it can only have 2 electrons surrounding it. And once you put a bond, those are the 2 electrons surrounding it. Okay? So it always has to go kind of on the perimeter of an atom. And the nitrogen started with 5 and then had the 3 hydrogens. So those 3 that were kind of by themselves, that's what's going to pair up with the hydrogens. So now you've got 1, 2, 3, 4 pairs surrounding the nitrogen. So you're all good. This also follows that guideline that things in the nitrogen column should have 3 bonds. Things in the carbon column should have 4. So this is the red, okay? So valence electrons are in blue. Carbon had 4. Nitrogen had 5. Chlorine had 7. Keep saying the bonds in my head. And then for the bonds, the carbon one's typically going to have 4 bonds. The nitrogen one's usually going to have 3. Chlorine's usually going to have 1. Those are really good guidelines to start with. They do not always work out perfectly, but they're very good general guidelines. Okay? All right, so with chlorine, when you look at the formula, CCl4, things are always going to, not always, things are usually going to behave as you would expect them. So looking at that formula, hopefully you would think the carbon should go in the middle and the chlorine should all surround it. I guess maybe you could have thought, switch to a regular marker. You could have thought it was something like, very wacko, like this, I guess, like all in a line. Let's see, that would be a chlorine. But if you did that, you would end up having to like bond 2 here, and then you've got like chlorines with 3 bonds. It just starts to get really funky. So most of the time, you're going to have, when you have something where there's one of one and then a bunch of another, then you're going to have the one in the middle, okay? Carbon is very often in the middle because it's going to make 4 bonds. Like if you had CCl2F2, okay, you look at it and say, well, I know carbon typically forms 4. The chlorine and the fluorine, those usually form 1. So it kind of makes sense that the carbon would be in the middle and the others would be around the outside. So those can be kind of hints to help you know the structure. When they start to get more complicated, like we're going to do acetic acid in a second, I'll give you the skeleton structure or like the general layout of what the molecule will look like. Okay? So once you know the general format of where the atoms are, then it becomes pretty easy to bond them for CCl4. You're just pairing up those electrons, and there you go. That's the whole thing. okay? C2H4, again, hydrogens can only form one bond. So they're going to have to be on the perimeter. Those carbons then are going to have to be bonded to each other in some way. So let's just start with creating single bonds and then see where we are. That's always a good idea. Just make single bonds first and then go forward. So hydrogens to the carbons. I guess you could say, well, why aren't there 3 hydrogens on one side and 1 hydrogen on the other? If you did that, you would end up with the carbon that had the single hydrogen would end up with like lone pairs on it. And we don't usually see that. We usually see carbon with 4 bonds and no lone pairs. Okay. Also, things do tend to be as symmetrical as possible. All right. So then carbon bonded to the other carbon, and now we've got the 1 electron remaining. You're never going to have unpaired electrons, at least not in this class. When you get to organic chemistry, if you do that, you might see those kind of in the middle of a reaction, but they're called radicals. They react really quickly, and so they're very short-lived. They'll just form something else. Okay, so we're going to pair up those guys as well and redraw this so it actually looks good. This is what your structure is going to look like. Okay, so 2 carbons double bonded and then those 4 hydrogens surrounding. Okay, so these should feel pretty easy at this point. They're kind of as you would expect. All right, let's do a couple more. We're going to do NO plus and CO3 2 minus. So big difference here is that there's a charge. So these are polyatomic ions, meaning multiple atoms, but they've either lost or gained electrons. So the way we're going to approach this is if you have a positive charge, that means you've lost an electron. So we're going to remove an electron, one of the valence electrons. We're going to remove it, and we're specifically going to remove it from the least electronegative atom. Because if any atom is going to allow an electron to be taken away, it's the thing that's not as good at attracting electrons, right? So on the electronegativity table, oxygen is 3.5 and nitrogen is 3.0. So in this case, we'd remove it from the nitrogen. And then we do that before we even start drawing the structure. If it's negative, we're going to add electrons to the more electronegative atom. All right, so knowing this, go ahead and take a shot at NO+. If you finish it before I'm ready, you can do CO3 2- as well. Okay, so nitrogen's less electronegative. I took the electron away from there, just one, because it's a positive one charge. And then I'm going to go start pairing them up. And initially it looks pretty good. You're like, oh, they both have 2 unpaired electrons. I'm just going to match them up and it's all good. The problem is nitrogen only has 3 pairs surrounding it. So its octet is not satisfied. Now, on Friday, we are going to talk about exceptions to the octet rule. So before we get there, I'm going to tell you carbon, nitrogen, oxygen, and fluorine. So these are in the second row, all in a row on the periodic table. Those guys will strictly follow the octet. It has to do with how small they are. They're really, really small. They are always going to have those s and p orbitals filled. Okay, so now we look at it and we're like, well, what can we do? Anytime something doesn't have its octet satisfied, we have to share electrons. That's how we satisfy the octet, is by sharing with somebody else. So what we're going to have to do here, and this is okay, this is allowed, we're going to take this pair of electrons from oxygen, and we're actually going to share the entire pair now with both nitrogen and oxygen. Okay, so you can never, except for when there's charge, you can never erase or add electrons, but moving them in order to abide by certain rules is fine. So we're going to move that pair into a bond. So we'll end up with a triple bond and a lone pair on each atom. Because that's the only way we can do it in order to satisfy the octet. When you have a charge, you are supposed to indicate that in the drawing. So you put brackets around it and put the charge on the outside, just like we did when they were ions. Okay, the thing that you'll notice here that we did kind of break is the guideline that nitrogen has 3 and oxygen has 2 bonds. Nitrogen works out well, but oxygen ends up with only 1 lone pair and 3 bonds now instead of 2 and 2. So that's okay, it's a guideline, but we do end up having to, not follow that because we need to follow the octet rule. Okay, this is a good time to introduce the idea of formal charge. It doesn't really change how we do this, but it's a useful example. So anytime that things don't follow that guideline of how many bonds they form, it's not great. It's kind of makes us wonder if the structure is really accurate, okay? So we have this system for showing when things don't behave the way we would usually expect them to, and it's called formal charge. And the way that we do it is we look at how many valence electrons the atom came in with. So I'm just going to say valence electrons atom had originally. And we're going to subtract off how many electrons it now has surrounding it. So by that, I do not mean the total number of electrons it's sharing, because obviously there's going to be 8, right? Like that's the whole octet rule. I'm talking about just the electrons that are right next to it. So by that, I mean I'm going to have these 3 electrons be assigned to oxygen, and I'll use green for the other one. These 3 be assigned to nitrogen. So each bond is made up of 2 electrons, right? We usually think of it as one came from the oxygen and one came from the nitrogen. In this case, we know they actually both came from the oxygen. But we're going to separate those out and count how many does it have now. It's almost like valence electrons that it has once it's in the molecule. That's, I think, how I describe it in the equation form that's on that previous page. Okay, so let's look at nitrogen, because nitrogen actually is 0. It starts with the same number it finishes with. So nitrogen started as 5, because that's what column it's at in the periodic table. And then it still has those 5 electrons. So just highlighting them. 1, 2, 3, 4, 5. Okay, so it gets to claim 1 from each bond as its electron. So that is actually ideal. A formal charge of 0. So I'm going to write that just like a little number next to the atom itself to indicate its formal charge. When we talk about things having a preferred number of bonds, like nitrogen wanting 3 bonds, it's to maintain the formal charge of 0. It's like it comes in with a certain number of electrons and it hangs on to that same number of electrons. Yep.
What's that word under has?
Surrounding it. Probably should lengthen that a little bit. Surrounding it. Okay, so now looking at oxygens. So let me erase the little equation numbers that I used for nitrogen. Now looking at oxygen. Oxygen has 5 as well, right? 1, 2, 3, 4, 5. But it started with 6. So 6 minus 5, we would say that oxygen has a -1 formal charge. Oh, sorry, +1 formal charge. Okay, so I'm going to write +1 there, which means it like has 1 less than it came in with. That should make sense, right? Because it took both of these electrons and turned them into a pair, one of which kind of was assigned to oxygen and one was assigned to nitrogen. So it's almost like it gave up one of its electrons to nitrogen. So that isn't ideal for them to have a non-zero formal charge, but sometimes it's inevitable. The other thing, especially in this case, why it's inevitable, is that the whole thing has a charge. So the total of all the formal charges, 0 and +1 in this case, has to be equal to the overall charge, which is +1 in this case. Like if we looked at the CCl4, if we did all the formal charges for those, they need to add up to 0 because the molecule is 0 charge. There's no overall charge on it. Now, formal charge can sometimes be useful for picking between multiple structures, like if you have 2 different structures and you're not sure which is the best one. But I'll tell you, for you guys, maybe there's an example that we'll go through, but almost certainly you'll be able to rely on the idea of the column is going to dictate the desired number of bonds. And if you can keep it at that, then you know that the formal charge is 0, and so you know that's the preference. So like a halogen, like chlorine, you're going to want it to have 1 bond and 3 lone pairs. And if it doesn't, you want to try to see if you can have a structure that, changes it so that it does. So hopefully on Friday we'll have at least one example where you have to use formal charge to pick between 2 structures and decide which one is better. But at least now you know how to do it. Okay, let's do another one. CO3 2-. Make sure you account for those extra electrons and take a shot at this one, the carbon being in the middle. If you have time, you could go ahead and assign formal charge. That might be interesting. You know, sometimes I feel for you guys and I'm like, it's probably so boring sometimes sitting here doing this. But like, at least you get to like draw pictures and do math problems. Like, I can't imagine sitting in like a history class or writing class and just like, I don't know, it sounds terrible. Maybe it's interesting for people to listen to that stuff. Okay, so if you want to check, make sure you have the right valence electrons and everything. Don't forget those 2 extra electrons. That's what I added in red, 1 on each oxygen. You certainly don't want to put them all on one atom. We know the oxygen's the most electronegative, so they are going to go to oxygens, but it doesn't matter which 2, but put them on 2. Don't try to put them on 1. And then we'll go ahead and draw bonds. So each of those oxygens gets a single bond, and then, you know, things work out nicely. In the examples we give you, very rarely are we going to give you something really, really weird. Now we have 2 electrons on the carbon, 2 electrons on the oxygen, so those pair up to satisfy the octet. I'm just going to redraw this so it's a little bit tidier. Always making sure to draw those lone pairs on there too. You can't just like, they're an important component. The reason why we care about Lewis structures so much is because it's a description of where all those electrons are. And remember, electrons are what is going to dictate chemical reactivity. So if we know there's a bunch of lone pairs on the exterior of this atom, and you get something else that comes along that maybe has, like a fluorine, that has lower available energy levels, those oxygen electrons might actually react with it and add to the fluorine rather than this molecule. So we're trying to figure out where those are so that we can then predict how they're going to behave. Okay, so the only other thing we need to add to this structure is the charge. But what about if you didn't draw the double bond on the top oxygen? Like, what about if you drew it on this oxygen? Well, it's certainly not wrong. In fact, some people might say, well, who cares? It's just like you turned the molecule, okay? Well, let's pretend like you didn't just turn it. Let's pretend like we could identify the 3 different oxygens. You can do this. We do this a lot with hydrogen. If you use deuterium, which is an isotope of hydrogen, so it's got 1 proton and 1 neutron instead of just that proton, you can identify like which hydrogen is which. So heavy water is often, they use deuterium to be able to identify the 2 hydrogens, or they might use it for both hydrogens. So let's pretend you use different isotopes and you could figure out which oxygen was each. So maybe I'll label them. Like this is oxygen 1, 2, and 3. And what we're saying is that what happens if we draw the double bond on oxygen 1 versus oxygen 2? And for that matter, let's go ahead and draw the 3rd version. Get rid of our messy one over here, which would be having that double bond on oxygen 3. Now, when I'm doing this, I'm making sure that the lone pairs match up, right? If it's a double bond, then it only has 2 lone pairs. If it's a single bond, it has 3. Because I've still got to maintain the 4 pairs, the octet, okay? Okay, so how do I know which one is right? Or for that matter, is there one that's right? Do you guys remember, I think it was in the video, that we talked about how, maybe it was on Friday. Anyway, how double bonds are shorter and stronger than single bonds. Shorter and stronger. And a single bond is longer and weaker. Okay? when we look at the actual structure of carbonate, CO3 2-, and by look, I mean we do quantum mechanical calculations, and that will tell us bond lengths and bond strengths. When we look at it, these 3 bonds, the ones to to oxygen 1, 2, and 3, are actually all equivalent. So there is no difference between the strength and length of any one of these 3 bonds. And in fact, they actually look like an in-between a single and a double bond. So they're shorter than a single bond would be, but not as short as a double bond. So there's something weird going on. And, after we knew more about chemistry, we figured out what it was, is that this extra pair of electrons that's making up this double bond is actually spread out over all 3 of those bonding regions. So it's called delocalization. It's a very stabilizing effect, like spreading out that negative charge so it's not all repelling against each other, letting it be attracted to multiple different nuclei, creates a very stable structure. And that's what actually happens. In fact, if we look at the bond lengths of these and bond strengths, they kind of look like 1 1/3 bonds. So that extra bond separates itself out 1/3 of a bond, which I know is bizarre to think of, especially when you remember that there's 2 electrons, but 1/3 of that extra pair ends up in each of those regions. So sometimes this is not official, but sometimes I like to draw this like this. So they've all got a single bond, and then the dotted indicates that extra 1/3 that adds up to the last bond, and it gets spread over all 3 of those bonds. Okay, so how do we draw it then to represent it? Well, unfortunately, we have to draw all 3 versions, and we use these little double arrows to indicate that it's all 3 of them all at once. So it's almost like an average of all 3 of those structures. So this happens anytime where you have a second or third or whatever bond that could be moved from one atom to another and not really look any different. So it couldn't be like if one of those oxygens was a sulfur, you wouldn't like swap it between the oxygen and the sulfur because those have very different properties. They're going to attract the electrons differently. But when you have equivalent structures that the only difference is really where you're placing that additional bond, then you need to draw all of the possibilities. And then the real answer to what is the Lewis structure of carbonate needs to be all 3 of these together. So this is resonance structures. Okay, I'm just gauging what I want to talk about. Let's just really quickly talk about, no, I don't want to do that on this one. Nah, that gets icky. Okay. Next one. This is acetic acid. If you guys remember when we wrote the acetate ion, we would often write C2H4, not H4, sorry, H3. C2H3O2. Same thing. It's just we're condensing all the atoms together. The reason we sometimes write it like this is to hint at what the structure looks like. So I'm not going to draw the bonds in for you, but I'm just going to draw like where the atoms are. So you go ahead and put the valence electrons in, but recognize that like these guys are going to be bonded to each other and this is going to be bonded to that. But that other oxygen is not bonded to the oxygen, it's bonded to the carbon, okay? So if I put the bonds in there for you, this would be what we consider a skeleton structure. it's not telling you the exact structure because all the electrons aren't in there. It's just telling you the general like order that the atoms come in. Okay, so I have all the valence electrons on there. I'm going to start putting bonds on now. This one actually works out pretty straightforward as well. It's just a matter of, you know, showing you guys how we might draw more complicated ones and like start them off for you, but not show you absolutely everything. So hydrogens are always the easiest. You just bond them to whatever they're next to. That's all they can do. We need single bonds on everything in order to make sure it's actually attached. And then we worry about the octet. And we see that carbon has that kind of electron that's hanging out. So does oxygen. So those guys get bonded. Obviously, we would tidy up this structure. Oops. And draw it like that. Okay, so double bond to that oxygen. So both of the oxygens still have two bonds. It's just that one of the double bonds is to a carbon and one is, you know, to two individual atoms. Okay, so that's what acetic acid would look like. All right, last one is this structure down here. I am going to actually complete the two structures. I want you to first tell me which one you think is right. And then I want you to assign formal charges to the main atoms, the carbons and the nitrogen. And then we're going to talk about kind of how formal charge proves that it's which one is right. Okay? So the first version is going to be a double bond here with a lone pair there. This is, if you went and drew all the valence electrons, this would be the right number of them. Or the other version is this. Okay, so select which one's correct. Then I want you to identify the formal charge on carbon, carbon, and nitrogen. And then we're going to talk through that. Okay, so remember for formal charge, it's like the original valence electrons minus, so we'll just say original minus the electrons it has now, like in the molecule.
Make sure it doesn't get destroyed. That's all. All right, well.
Okay, so first structure, the carbon, so I'm just going to go in order. The first carbon started with 4 and has 1, 2, 3, 4. Okay, so it's the same, 0 formal charge. Next carbon, 1, 2, 3, 4. Okay, 0 formal charge. And then the nitrogen, 1, 2, 3, 4, 5. Started with 5, ended with 5. Okay? At first you're like, well, that's uninteresting. This is what we would expect. So if it has the number of bonds that corresponds to the column, like carbon has 4, nitrogen has 3, as long as it has the correct number of lone pairs as well, then the formal charge is going to be 0. Formal charge of 0 is ideal. It is the most correct drawing that we could represent it with. So your initial reaction should be that this was the best one. And given the formal charges, it probably is, but let's just double check on the bottom one. So the first carbon, 1, 2, 3, 4, 5. So that has a formal charge of -1. The next carbon, 1, 2, 3, 4. Okay, that one's 0. And the nitrogen, 1, 2, 3, 4. So 5 minus 4 or +1. So this is formal charge is a good example of how it's like a proof that that one is better than this one. It's not adequate to just say, oh, it has the same number of bonds as we predict. This is like really showing us mathematically that having those number of bonds is correct, the correct way to do it. Okay? All right, we'll do more stuff, more Lewis structures on Friday.
This is a dumb
I'm sure it's not.